In 8.6, we are going to talk about probability. We will find probabilities of events, find probabilities of mutually exclusive events, and then find probabilities of independent events. So the probability of an event is any happening whose result is uncertain is called an experiment. Possible results of experiments are outcomes, and the set of all possible outcomes of the experiment is the sample space. Any subset or subcollection is an event. So, for instance, when a six-sided die is tossed, the sample space is represented the numbers 1 through 6. And for the experiment to be fair, each of the outcomes has to be equally likely. So, if we look at this first example, we're just going to determine sample space. So, a sample space is kind of the outcome that you could have based on whatever's going into it. To describe a sample space in such a way, each outcome is equally likely. You must sometimes distinguish between or among various outcomes in ways that appear artificial. So for example one, if we want to find the sample space for part A, if one coin is tossed, we will say that your sample space, or S, if one coin is tossed, you could either have heads or you could have tails. So that would be your sample space. If two coins are tossed, you could have heads and heads, heads and tails, tails and heads, or tails and tails. And then if three coins are tossed, we could have heads, 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 tails, heads, tails, heads, tails, heads, heads, tails, heads, tails, 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 heads, or tails, tails, tails. So that one's a little bit longer there. So the probability of an event. So if your event E has n of E, which are your equally likely outcomes, and its sample space is n of S, so the number of equally likely outcomes. So this is your number of equally likely outcomes. I don't know where I was going on this equally here, sorry. I was throwing some extra letters in there. So equally likely outcomes. And this n of S is the number in the sample space. So your total number of outcomes that you could have. And you divide those, and that gives you your probability. Your probability always has to be between 0 and 1. If it ends up being 0, then that means that there's no chance of the event happening. And if the answer is 1, then that means that there's a 100% chance that event will occur. And that's kind of what this table is talking about right here. So for example 2, we want to find the probability of the event where two coins are tossed. What is the probability that both will land heads up? So let's first think about that sample space that we had when two coins were tossed. So we have heads, 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 tails, tails, heads, and heads, heads. Right? So this S, we know we have 4 possible outcomes. So when we look for the probability, our total number of possible outcomes is in your denominator, and the number of events within that sample space is in your numerator. So both landing heads up, there's only one event where they would both be heads up. So we would say that the probability is 1 in 4. If we look at B, we have a card is drawn at random from a standard deck of playing cards. What is the probability that it's an ace? So we know that our sample, we have 52 cards total. And of those 52 cards, we want to know the probability that it's an ace. So our probability, we know that there's 4 aces in the deck. So we could have up to 4 chances to draw out of 52 cards, which would end up being 1/13. So when we talk about mutually exclusive events, so two different events, A and B, that are from the sample space, are mutually exclusive when A and B have no outcomes in common. So in the terminology of sets, we would say that the intersection, that upside down U means intersection. So the probability that A and B will be the same or that is 0. So for instance, if 2 dice are tossed, the event A of rolling a sum of 6 and the event B rolling a sum of 9 are mutually exclusive. Because when you roll 6, that doesn't affect if you would roll 9 in another roll. So to find the probability that one or the other of two mutually exclusive events will occur, you add their individual probabilities. So if A and B are events in the same sample space, then in general, you could say if they're in the same sample space, you would do the probability of A plus the probability of B, but then you would have to potentially subtract where they could intersect if there's a union between those two. But if they're mutually exclusive, then we know that that union of A and B is 0, and so you would really just add those separate probabilities. So the probability of a union, this is kind of going back here, this first one here, this probability of a union. That U means union. So we have one card is selected at random from a standard deck of 52 cards. What is the probability that the card is either a heart or a face card? So if you look at this Venn diagram they gave you, they listed all the hearts, and in the pink one, they listed all the face cards, and there's this overlap of hearts and face cards. And so if we want to find the probability of it either being a heart or a face card, so what we have to do is first find what's the probability of it being a heart. Right? So the probability of a heart is 13. There's 13 of the 52 cards are hearts. And then the probability of a face card, right? 12 of the 52 cards are face cards. And then we have the probability of both. So when you look, 3 of the 52 have both of those characteristics. So if we wanted to find the probability of the heart and the face card, we would have to take the probability of the heart, so 13 over 52, plus the probability of the face card, 12 over 52. But then we have to subtract the overlap. So subtract the 3 over 52. If you do that, you get 22 over 52. Or if you were looking for a decimal, we would say about 0.423. And then the last topic we're going to talk about with probability is the independent events. So two events are independent when the occurrence of one has no effect on the occurrence of the other. So for instance, rolling a total of 12 with two 6-sided dice has no effect on future rolls or outcomes of future rolls. So if we want to find the probability that two independent events will occur, we're going to multiply the probabilities of each. So if A and B are independent, to find the probability that A and B will occur, you just do the probability of A times the probability of B. So if we look at this example, it says a random number generator on a computer selects 3 integers from 1 to 20. What is the probability that all 3 numbers are less than or equal to 5? So if we let A represent selecting a number from 1 to 5, right? Because less than or equal to 5. So if we say that so the probability of A would be selecting a number from 1 to 5. Out of the numbers 1 to 20, we could have 5 out of 20 of our numbers, right? And this is representing selecting oh my gosh, I can't spell today. SELECT. Selecting a number from 1 to 5. Right, so we're going to say that that's our A. And then the probability that all three numbers are less than or equal to 5. Oh, sorry, I underlined the wrong part. So the 1 to 5. So the 1 to 5, we do have that less than or equal to 5. But then we want that all three numbers. So the probability of each time is going to have that same probability. So if picking one number from 1 to 5, the probability is 1/4. Then picking the next number will also be 1/4. And then picking that last number will also be 1/4. So our probability that all three would be under 5 would be 1/64.